Hello everyone, and welcome to the next video in the series. This is a technical skills video on the topic of multiplication and division of numbers that are written in scientific notation. And to begin, I would like to talk about how we work with exponents of 10. So for example, if we multiply by a number that's written in scientific notation and it has a positive exponent of 10, we pretty much know what happens actually. In this case, decimal point moves forward over 2 digits. And it could be the case that we multiply by a number that's written in scientific notation with a negative exponent of 10. And we also talked about what that does. It basically moves the decimal point back over 2 digits because a negative exponent of 10 implies repeated division by 10. If you divide by a number that's written in scientific notation with a positive exponent of 10, then you're dividing by, like in this case, you would be dividing by 100, and decimal point moves back. Now this is interesting because the behavior is the opposite of multiplication, which is what's expected because multiplication and division are inverse operations. So when you multiply by 10 to a positive exponent, decimal point moves forward. But if you divide by 10 to a positive exponent, the decimal point moves backward. And of course, it could be the case that we divide by a number written in scientific notation with a negative exponent of 10. Now, we could argue that this is the opposite of multiplication by 10 to the power of negative 2, and therefore decimal point moves forward. But I would like to put a bit more meaning into this, so that you have a better understanding of why is it that when we divide by a negative exponent of 10, decimal point moves forward. Okay, so this has to do with a kind of a what I call micro skill that you should know very well. These kinds of micro skills are the kinds of skills that I've noticed that people who seem to be better at math usually have them. They're not the kinds of skills that you use all the time, but they appear with enough frequency, and they help a lot in trying to shed light on what's happening as you work with mathematical entities. And one of these is if you divide a number like 8 by a fraction such as 1/2. So basically what this says is how many halves fit in an 8. That's the meaning of the division. How many halves fit in an 8. And if I can show you a diagram as to what we are talking about, let's say that this is 1 and therefore this will be 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. And the question is how many pieces of this size, that's a half, fit in an 8? And the answer, I think, if you think about it a bit, would be that there will be twice as many. And therefore, the answer really is 8 times 2. We would expect 16 of them to fit. 2 fit in 1, and therefore 16 fit in 8, which is 8 times 2. And what you notice is that we could think of this as division by a half turns into multiplication by 2. Okay, problem number 2. And this problem says that we have 8 divided by 1/10. And we could sort of think of this as in problem number 1 as to how many tenths fit in an 8. And here I have another diagram for you. Now again we have on a line we have the numbers 1 to 8, 1, 2, 3, 4, 5, 6, 7, 8. And now this time I've divided the distance from 0 to 1 into 10 parts, and therefore one part is 1/10. And one of these tiny divisions that you see here is a 10th. So the question is how many of these fit into an 8? That's what this is. How many tenths fit in an 8? And the answer would be 10 times as many, because 10 of them fit in 1, and therefore we get a total of 80 of them in 8, which means that we have 8 times 10. And again, you notice that division by 1/10 turns into multiplication by 10 on the other, or you can turn it into multiplication by 10. And therefore here's a highlighted version of that. Division by 1/10 becomes multiplication by 10. And we can go on like this. We can divide 8 by 100th, and that means how many hundreds fit in an 8, and the answer would be 100 of them. So division by 100 turns into times 100. Okay, now we could write 100th in different ways, of course. Instead of 100, I could use 10 to the power of 2. That's the same as 100. And if we do that, and sometimes we do, we would use 10 to the power of 2 here as well, just to have uniform notation. And therefore, it would become 8 divided by 1 over 10 to the power of 2, which is 8 divided by 100. Is the same as 8 times 10 to the power of 2, which is, again, 10 to the power of 2 is 100. So this is the same as 8 times 100. So really, these two say the same thing, but using different notation. One of them decimal notation, one of them uses 10 to the power of 2. And keep in mind that 1 over 10 to the power of 2, which implies that we have repeated division by 10, can be written down as 10 to the power of negative 2. So I could write down 8 divided by 10 to the power of negative 2 here. And I would end up with 8 times 10 to the power of 2. So that shows that when you have 10 to the power of negative 2, in effect, you're asking how many hundredths fit in an 8. And the answer would be 100 of them. And therefore, the exponent of 10 switches sign. Division by 10 to a negative exponent becomes multiplication by 10 to a positive exponent. Okay, so now with this knowledge, we know that if we multiply by 10 to the power of 2, decimal point moves forward over 2 digits. If we multiply by 10 to the power of negative 2, decimal point moves backward or to the left over 2 digits. Division is just the opposite. If I divide by 10 to the power of 2, decimal point moves back over 2 digits. And if I divide by 10 to the power of negative 2, it turns into times 10 to the power of 2. And therefore decimal point moves forward over 2 digits. Now let's see how we can use all of this together. Let's say we are multiplying by 10 to the power of 3 and then times 10 to the power of 4. We could argue that what this means is that we are multiplying by 10 to the power of, so first of all we would move the decimal point forward over 3 digits, and then we would move this decimal point forward over an additional 4 digits. And so we would end up with times 10 to the power of 3 plus 4. You notice that what's happening with the exponent is that it's keeping track of how many places the decimal point is moving over. So in times 10 to the power of 3, decimal point moves forward over 3 digits. And then in times 10 to the power of 4, we move it again over 4 more digits. So in total, we'll end up with 3 plus 4 digits, or 7 of them. So this could be simplified to 10 to the power of 7. Problem number 2. Now, one of the exponents is negative, and keep in mind that that means repeated division by 10. So we can write down that this is equal to 10 to the power of, first, the decimal point moves forward over 3 digits, but then decimal point moves back because we are dividing. It moves back over 4 digits, and so we get 3 minus 4. The balance is 10 to the power of negative 1, which means in the balance, after you've done your movements, it's like you moved back over 1 digit. Problem number 3. Now we have times 10 to the power of 7 divided by 10 to the power of 3. And we can write this down. Keep in mind that this means, this is something else you should know. When you multiply by a division like this, you can think of it as multiplication by the top and then division by the bottom. So because we are multiplying by 10 to the power of 7, we can say decimal point moves forward over 7 digits. Division by 10 to the power of 3 actually moves the decimal point back over 3 digits because it's division by 1,000. And so we now subtract 3. You notice now that whatever we divide by switches sign. So if it's positive, decimal point moves back and we get minus. If this was negative 3, then decimal point would move forward and it would become plus. So really what it comes down to is whatever's on top, you keep the exponent sign as it is. Whatever's in the divisor, you switch the sign of the exponent of 10. Okay, so this gives me 7 minus 3. So in effect, on the balance, decimal point would move forward over 4 digits. Problem number 4. Now this time we are dividing by 10 to the power of negative 3, and keep in mind that the decimal point moves forward. So the quick way is to say 10 to the power of 7 and then plus 3. So again, any sign in the exponent of 10, if it's in the divisor, switches. Here's number 5, where we have all kinds of stuff. So now we have 10 to the power of 8, a positive exponent on top, a negative exponent on top, a positive exponent down here, and a negative exponent here. And for this we get 10 to the power of decimal point moves forward over 8, back over 2, back over 4, and forward over 5. So again, the 8 and the negative 2, which are on top, kept their signs. 4 and negative 5, which are down here, switched signs. Now 8 minus 2 is 6, minus 4, 2, plus 5, 7. So in effect, we end up moving the decimal point forward over 7 digits. Okay, now that we know how to work with exponents of 10, we can talk about multiplying numbers in scientific notation. So because multiplication can be done in any order, we choose to multiply the significants, in this case 4.5 and 2.1, separate, and then we multiply the exponents of 10 next. If I multiply 4.5 by 2.1, I will end up with 9.45. And then we work with the exponents of 10. We have times 10 to the power of decimal point moves forward over 3 digits, and then it moves forward again over 4 digits. So we end up with 9.45 times 10 to the power of 7. Problem 2. Now we have 3.2 times 10 to the power of negative 3 divided by 2 times 10 to the power of 4. And therefore we do the division, 3.2 divided by 2. That gives us 1.6. And then times 10. Decimal point moves back over 3 digits, and then it moves back again over 4 digits. Keep in mind that the exponent of 10 switches sign when you try to account for which way the decimal point moves. Alright, and this gives us 1.6 times 10 to the power of negative 7. So in effect, the decimal point moves back over 7 digits. Now here we have 4 numbers, 2 on the top and 2 down. Keep in mind that when we divide by a product, it's like individual divisions. So now we do 2.5 times negative 3 and then divide by 5 and then divide by 4. And if we work out the significance, then we end up with the number negative 0.375. Then we have times 10 to the power of 6. Note how the sign of the exponent on top does not change, the ones down switch. Decimal point moves forward over 6, back over 2, forward over 1, back over 3. And so we get negative 0.375 times 10 to the power of 2. Now this is not in scientific notation. We need to move the decimal point forward, and then exponent comes down by 1. And therefore we end up with negative 3.75 times 10 to the power of 1. Okay everyone, and that's the end of this video. Thank you again for watching, and I'll see you in the next video when we will go back to the problem solving skills component of the program, and I will talk about problems that require that we work with a percentage of a quantity. A very interesting video on working with money problems is coming up along the way. Thank you so much for watching again, and I'll see you in the next video.